state of polarization transmission over for mitigation of fiber non-linearities. So basically, I'll take over what Yuna was talking about and show basically a different method or a different metric that we can or should look at or should consider as well. So the motivation is the same one again. So we basically have Kerr non-linearities that make our observed SNR go first, or well, first of all, with increase of laser power, our observed SNR goes up, and at some point the non-linearities kick in, and then the observed SNR is peaking and is going down. So basically, the motivation of what Yunus is doing, and what all of us are basically doing at the moment, is to bring this peak a bit higher. And so this is basically what we're trying to achieve here by avoiding non-linearities. Okay, something else that was, I guess, also mentioned is that we want to have some sort of flexible signaling, which means that we only select a subset of transmission sequences, and then we can basically trade something like the nonlinear effects that we create versus the transmission rate that we want to use. Okay, so now what I'm going to show you next is like my nail that I'm hammering on with it's kind of the same methods. So I'm looking at the state of polarization. From physics, well, I didn't have it too much, but I heard that you learn in physics that you can talk about Stokes parameters when you're working with lights, and so it's basically the intensity, and then there's 3 parameters that show you how the polarizations work together, and so those is what we see here is the state of polarization for dual polarized signal point. So you see 2 QAM or QPSK symbols. So here they're on top of each other, and there you have one here and one here, for example. So, and you see that what the state of polarization looks like is for one row. It's the same. And so there's a nice patent and some papers from Roberts that found out that you can reduce the nonlinear noise when 2 consecutive 4D symbols have minimal state of polarization when you add them together. So, okay, what does that mean? So basically, it means if you well, they would claim if you select one of those points at the first transmission, then you should better take one of those symbols at the second transmission, because if you look at the state of polarization, so the 4 is always the same, but the third entry is here, it's 4, and here it's -4, and when you add them together, then basically that collapses, and for some reason this is beneficial. So for QPSK, you can actually use a sort of proxy. So you have here four degrees of freedom in that sense, although you have eight dimensions. And the fun thing is that you can choose 3 of them freely, and the 4th basically determines if your signal will be bad or if it will be rather good. So so this is some nice thing to notice. Okay, as I said, I'm not the one who came up with this idea. So there's a constellation called polarization balanced dual polarization QPSK. Okay, so it's getting very long. So they were just repeating what I showed on the last slide. They were saying, okay, we have a set of 8D again over 2 time instances constellation points, and some of them are are good, the ones that add up to 0. Some of them are, well, mediocre and some bad consolation points. Okay, we'll just take the good ones. That's a reasonable choice usually. Then there came other guys that said, yeah, okay, this is a very, very low rate. So what we should do, we should take the good points and we should take the medium points. And you could continue like that. But we are suggesting with our tools, our hammers that we have is, well, why don't we assign probability to those? Okay, so we want to use the good points. We want to use them often. We want to use the bad points less often. And okay, the mediocre ones also some probability. Now a question would be, well, how do we get to those probabilities? For those energy case, it was kind of obvious. So, but what we basically did there was to define a cost function, and for energy, this cost function led to this Maxwell-Boltzmann distribution. So for this AWGN case, and well, we can also here we could come up with a cost function, and here we would actually use this delta to put in not the signal itself, and then not take only 1 point from our set, but take all of them basically, but with different probabilities. Okay, so we can build that. So it's basically with the tools we know from this probabilistic amplitude shaping, it's rather direct. So at the very end, we want to have our symbols with this with the certain probabilities on the state of polarization. I told you before that basically 6 dimensions or 3 symbols, 3 2D symbols we can select as we want to, and this means we can put parity bits in there, anything like that. Just the interesting part is the last 2D symbol, which is here this odd those odd Ys, and those we obtain by using a source that gives us those deltas with a certain probability that we want according to the cost function that we chose. And this is basically then how the scheme would look like. Something useful to check is what happens at this edge cases. So now imagine that here, for example, I choose a uniform distribution. Then what we obtain actually in the end is that we're back to QPSK. We have no shaping overhead attached, so that is fine. What happens if we fix the distribution to something to the best delta that we can have? So that was pi here. Then actually the scheme collapses again to this polarization-based dual polarization, polarization balanced dual polarization QPSK case, and we have exactly the same rate as before. Okay. So so we've done our methods. So now we are looking at some simulation results. Something important to notice is I use dispersion managed fiber. This is unfortunately rather crucial for this because here the method works really well. So dispersion managed means that we're basically trying to inverse the dispersion again, and by applying some fiber strings that have negative dispersion, for example, and in those scenarios we can gain quite a bit. So we use here 60 points spans of large area, large effective area fiber linked with 75 kilometers at each spans. There was eight lasers. So the effect from neighboring lasers has to come in as well. And we have a grid of 150 gigahertz and 120 gigabaud, and an RC with 25%. And here we assume a perfect chromatic dispersion compensation after each span. what this does with our link is so here there's two reference curves. This is the uniform curve. This is the other extreme case when we select only some symbols, and the ones in between are twofold. So you see this. So this blue curve is basically we select a few constellation points more, then we arrive with this blue line. Then we have something like a time sharing. So we take either all symbols or just the good ones. Then we're basically on top. But if we use this the shaping techniques, then we can gain a bit when maintaining the same rate. So bringing this curve, so bringing those maxima that we show here together over different rates. So you see we fixed the rate here to 0.857 bit per real dimension. Then if we do this over the rates from a quarter, no, 3/4 to 1, then you can see, okay, for the case that we at 3/4 we see the highest gains, but also for something in between there's rather a high gain of this probabilistic shaped version over the time sharing, which is as flexible as our so. Okay, so with this, so I would like to conclude that we've shown like a new possibility to shape sequences that work very well for dispersion managed fibers, and using those the state of polarization as a metric that we want to optimize. Thank you.
Yeah, thank you. Let's thank the speaker. So, any questions? Yes, please.
So thank you for the talk. I guess this question maybe goes to all of the presentation. So you trying to avoid the non-linearities, but in some cases maybe you are like making other effect worse, like how about phase noise? So if you are putting two signal or two constellation point close to each other, then they will be more vulnerable to phase noise. And here, like also the, I guess the polarization mode dispersion, how it will also affect this if you have if you send these signals into orthogonal polarization. Yeah, this is my question.
Okay, so I guess so to be fair, so with the other speakers, I think a fair method there would be to look at the generalized mutual information or the mutual information, so which most of us did. Here I didn't. So the question is actually rather relevant. So if you look at those metrics at the very end, I think it's fair. So then you see a real improvement, or if it didn't really improve. Yeah, for here how the polarization mode dispersion will come into play, I actually can't tell how it will behave. So sorry for that answer.
Thank you.
Okay, one more quick question. 1 minute.
Very quick. Can you generalize this to say 3 bits or 40 bits per real dimension? Something more spectrally efficient?
So so that's true. It's the number of bits is rather limited. We're working on that.
Okay, let's thank the speaker again.